Okay, we're going to take some notes today, or I'm going to give you some notes. And the goal of this lesson is to discuss a theoretical approach to probability. Okay, now the theoretical approach is different than the experimental approach. The experimental approach is you look at a lot of trials, and over time, the experimental probability should approach the theoretical probability. So then what is the theoretical probability? Theoretical probability is really more so based off of math or slash outcomes. Okay. And theoretical probability is not much of a mystery. For example, if I said you're rolling two six-sided dice, I should say six-sided, and suppose that these are fair dice and adding the faces together, okay, what is the probability that the sum is even, the sum is less than six, the sum is prime? Okay, so I have three probability questions I'm asking you to address. Okay, so there's a lot of different ways to answer this question, but if you don't know much, one of the very first things you're going to do is think about your list of every possible outcome. Okay, and that list of all outcomes is called your sample space. So your sample space is just a list of all of your possible outcomes. So for example, I have two six-sided dice, okay? So I have die one, which can be any of six different things. I have die two, which can be any of six different things. So because they're happening together, I have 36 different outcomes. Okay. And there are lots of ways to come up with these 36 different outcomes, but I'm going to just list them this way. So I have die one, two, three, four, five, six. Okay. I should have written that over there. And I have die two. Okay. One, two, three, four, five, six. So for example, this is 1, 1. This is 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. Okay, very poor that I didn't give myself nearly enough room for that. 2, 1, 2, 2. I'm squeezing this all in here. 2, 3, 2, 4, 2, 5, and 2, 6. Okay, and you'll see that if I keep listing them out, I'll have 36 total outcomes when I'm all said and done. So 3, 1, 4, 1, 5, 1, 6, 1. Okay, 3, 2, 4, 2, 5, 2, 6, 2, 3, 3, 4, 3, 5, 3, 6, 3, 3, 4, 4, 4, 5, 4, 6, 4. Okay, 3, 5, 3, 6. Make a little bit more room for myself. Sorry if this is sloppy. Well, I know it's sloppy. 5, 5, 5, 6, 6, 5, and 6, 6. So there are my 36 different outcomes. Now, there are some obvious questions here. Well, Mr. Russo, getting a 1, then a 2, should that be counted differently than getting a 2, then a 1? Well, of course it should. Because if you think about it, there are two different ways that you could get a sum of 3 on two six-sided dice. The first die could be a 1, while the second die is a 2, or the first die could be a 2, and you could still get a sum of 3 if the second die is a 1. And then that follow up question is, well, what about a 1 and a 1? Should you count that twice? No, of course you shouldn't. A 1 and a 1 can only happen once. Both dice must be ones. Okay? So if it's a 2 and a 1 versus a 1 and a 2, those are different. But a 1 and a 1 is the same as a 1 and a 1. That's counted only one time. Okay? So there are my 36 different outcomes. Okay? And these 36 different outcomes happen to be equally likely. And what that means is that each outcome has the exact same chance of occurring. Pretty sure I'm spelling occurring wrong there. But every outcome has the exact same chance of occurring, 1 in 36. Okay? And now it's very easy to go back here and say, okay, what's the probability the sum is even? Okay? Let's count the number of outcomes that lead to an even sum. All right? So we're going to go to that's even, right? Even, 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 and even. And it ends up being 18 of the 36. So 18 outcomes have a sum that is even out of 36 total outcomes, which is 1/2. Of course, it's 1/2. So probability sum is less than 6. Okay, let's count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 out of 36, which is just 5/18. And last but certainly not least, the probability the sum is prime. The smallest prime number is 2, so 2, 3, 5, 7, 11. Okay, 2 is 1, 3 is 2, 3, 5 is 4, 5, 6, 7. 7 is 8, 9, 10, 11, 12, 13. And 11 is 14, 15. So there are 14 out of 36 total outcomes that have a sum that is prime. Okay, so one of the points of what I did here is to say, if I give you a problem and ask you to determine some probabilities, you may want to list out the sample space. Okay, listing the sample space of outcomes makes it very, very easy to determine those probabilities. Ridiculously easy. Okay, you just have to list them all out. Now, sometimes that could take a little bit of time. It could be a little tedious, but it's never really ridiculously hard. Okay, if your number of outcomes gets to be a lot, 36 isn't that many, over 100 is probably a lot, you don't want to list out 100 different outcomes. Maybe that's when you start thinking about, is there another way to do this problem? Some other basics, okay, about probability, okay. S is a simple way of saying the sample space, okay, and just very simple. The sum of the probabilities of all of the outcomes in the sample space must equal 1. Of course, it must equal 1, okay? And secondly, the probability of any individual outcome has got to be between 0 and 1. So the probability of any individual outcome cannot be less than 0, cannot be greater than 1. Right? No problem. Okay? Now, let's talk about complements for a moment. Okay? In probability, if I have some event A, okay, let's say event A, okay, then A complement is A not occurring. Okay? So, let's go through a couple of examples. A is the probability the sum is even. Then the complement would be the probability the sum is odd. A is the complement, or sorry, A is the event that the sum is prime. A complement is the event that the sum is not prime. Okay? Let's let A equal the event that the sum is less than 5. Then A complement would be the event that the sum is greater than or equal to 5. So think about that last one for a moment. A complement is the probability the sum is greater than or equal to 5. So less than 5, not less than 5 is greater than or equal to 5. Okay? So be careful with those with regards to complements. Make sense? Okay? Last but certainly not least, a rule regarding equally likely outcomes. Okay? We actually already talked about that before. That is just us saying that the probability of some event is equal to the number of outcomes that fit divided by the total number of outcomes if the outcomes, if and only if the outcomes are equally likely. Okay, so what did I cover here that was likely the most challenging thing? This complement rule. Believe it or not, this complement rule is one of the most important pieces to what we did. And in me teaching this way, I totally forgot the biggest idea of the complement rule. The biggest idea of the complement rule is that if you have two complements, the probability of A plus the probability of its complement must always equal 1. Think about that for a second. The probability that A happens plus A not happening must equal 1. Because remember, the complement of A is everything else. Okay? That complement rule might be the most important piece of what I taught you, and likely the piece that you're going to learn, use the most in coming days, and maybe the piece that might confuse you the most in coming days. So that piece right there, that complement rule, put a star next to that. But going back to the math that we did here, just listing out your outcomes and answering a question by looking at your outcomes. Okay, so that is my lesson for today. Good place to stop, and have a good one, everybody.